Okay, got it. All right, so welcome everyone to the Probability Victoria seminar. Today we're extremely happy to have Jim Pittman from UC Berkeley. Jim is very well known, so I'm not going to give him an introduction to embarrass him, but yeah, anyway, I'm sure we all know him and he's had a long and great career. Jim, go ahead.
Well, thank you, Nathan, for the introduction, and it's a pleasure to see many old friends in the audience. I want to talk about something that I've been, thinking about for the last couple of years. I'm not really sure what I'm going to do with this. People tell me I should write a book, but I absolutely refuse to write a book. I'm trying to condense this into some kind of an expository article, or anyway, I'm interested. If any of you have ideas about what I should do with this, I welcome them. One of the things, of course, is to put it in the trash basket. I'm not sure what the electronic equivalent of that is, but we shall see. So my title is, or my main theme is what I call Euler's X-blog recursion or X-blog correspondence. And everyone in the audience is undoubtedly familiar with some form of this. But I would be surprised if everyone knew all the different forms that this might take. And I find it rather fascinating, the different ways that it arises. So by way of motivation, let me mention that the mathematics involved here, its most ancient form that I'm aware of is very classical relations between roots and coefficients of polynomials, which due to Girard, Newton, Waring, Jacobi, and it got folded into the theory of symmetric functions, which, 17th and 18th century, 19th century mathematics knew pretty well. It's not so well known to probabilists now, but certainly combinatorialists work in symmetric functions and know about what's going on there very, very, very deeply. Much better known to probabilists is the way that X-log relation appears in connections between moments and cumulants, which dates back to Thiele in the 1890s. Thiele essentially reinvented or was perhaps guided by what was known classically about roots and coefficients, and set the modern definition of cumulants. And then there's what seems like a completely different thread of combinatorics of partitions and permutations, which goes back to Cauchy and Jacobi. Then there's fluctuation theory of random walks and Lévy processes, and quite a lot of discussions around exponential formula in infinitely divisible distributions. And in each of these cases, you have the same functional relation, which I've written down here. It's the exponential formula, 1 plus some generating function that doesn't have a constant in it is the exponential of another generating function, r of x, which also doesn't have a constant in it. And well, I've started to call this relation or formula the Eulerian elephant, due to its many interpretations, and also the rather amusing poem, The Blind Men and the Elephant, which I recall: the 6 men of Indostan to learning much inclined, who went to see the elephant, though all of them were blind, that each my observation might satisfy his mind. So here we have the 6 men of Indostan and the elephant, and you see this man has found a tail. He thinks the elephant's like a tail. This man has found the side of an elephant. He thinks it's like a wall. Here's a man who's found a foot. This man found an ear. This man found a trunk. No, this man found a tusk, and this man found a trunk. So these are also totally different aspects of what is, to us, obviously the same animal, but to the blind men, perhaps not so obvious. Whatever. Let me start with the forms of exp and log that everybody from advanced high school, when I went to Australia, maybe when I was in Australia, it was advanced high school. By now, it's perhaps lower level undergraduate mathematics, we understand the e to the x or exponential of x as a limit of 1 plus x over r to the r as r goes to infinity. And we easily from that get the exponential series. So that serves, either of those serves as an acceptable working definition in the first instance for real numbers x, and then commonly for complex numbers, and often also for matrices and more fancy things. Once you have that definition in place, you start to think of logarithm as the inverse function of the exponential. So there's the functional inverse relations. And one way or another, you discover the power series for log. Historically, one of the fascinating things is that the power series for log was discovered before the one for exponential, because people wanted to integrate 1 over x, and they didn't have a formula for how you integrated 1 over x, and they basically defined it to be log. And that's actually a modern calculus definition of log, is to integrate from 1 to wherever, and that's your definition of log. Then, of course, exponential is the inverse of that. But one way or another, you discover that there are these 2 power series which are intertwined by a functional inversion relation. And you also learn basics of what happens when you differentiate them and what happens when you integrate them. And I've just written down some familiar formulas. So Melbourne is a city of trams. And if you live in Melbourne, you should appreciate the tram tracks metaphor. This is what I teach all my undergraduates. The most basic thing you need to know about exponentials and logarithms is what their tangent lines are. And there's x plus 1, x, and x minus 1. And you have the tendencies, and a kind of a stripped down version of the tram tracks picture is reduced tram tracks, where you are focusing more on the functions e to the x minus 1, x, and log of 1 plus x. And now you have, well, you don't have tram tracks anymore. You just have one straight line, the identity function, and the 2 graphs flip across there. So certainly this is the way I encourage my undergraduates and even graduates to think about the exponential function in the first instance, is through some graphical devices like this. But this picture doesn't do anything to help you understand the power series and what exponentials are doing with sequences. That's another aspect. So I believe that Euler was the first to think seriously about what exponentials and logs did to sequences. This is a copy of a page from Euler's 1755 calculus text. And this is his presentation of the functional relation, which we would now write, or he wrote even recognizably as S is e to the r of x, and it's 1 plus u of x. So here you can see, here is his first line, S equals e. E for Euler, he invented the notation. And there you have alpha x plus beta x squared plus dot, dot, dot. And then there's some Latin, which we needn't worry about too much. This mathematics is transparent, even if you don't know the Latin. You then write down that S is a power series by itself, and you use some fancy Gothic symbols, Gothic A, Gothic B, Gothic C. And then you have to understand that L is log. I think LS means you've taken the log of S, and then you differentiate, and then you use the chain rule, and you equate some coefficients. And in the end, you get a recursion, which tells you that if you have a functional relation of e to 1 power series is 1 plus another, then the coefficients have to be related. And this is how Euler writes it. It's pretty clunky with the Gothic and Greek letters, but it's very clear that he could write down any number of these. This is Euler's signature ampersand C, right? And so on, right? Any idiot can complete the table to any desired depth once Euler's got you started. So here's a slightly more modern version of, a LaTeX rendering of Euler's 1755 calculus text. He writes down exponential of 1 power series is another power series, and then you sort of think about what that could possibly mean. In modern language, Euler's alpha, beta, ... and even the x are commuting variables or indeterminates. And if you're rigorous about it, or think about these things as having values somewhere, they can take values in any field. It could be rationals or reals or complex. And in fact, it could even be a commutative Q algebra, which is a commutative ring that contains the rationals as a subring and has the additive and multiplicative identities, what you think they are, the usual 0 and 1 in the rationals. So somehow this relationship, Euler didn't say, I mean, he was perhaps smart not to say what alpha and x, and he didn't say what, he just wrote down this, what is now called a relation of formal power series, and proceeded to manipulate the relation to obtain identities involving the coefficients. So as I say, this is, Euler's formula is an identity of formal power series, and formal power series have been rigorously studied in this century by many, or last century, by many mathematicians. I mentioned some of them. And the nature of the identities that are involved, they involve identities between polynomials and several variables with rational coefficients. And it's a very handy fact that such identities, if they hold for integer arguments, they will hold also for variables in any commutative Q algebra, more or less whenever they make sense. So it is commonplace that you can work with formal power series and prove things for integers, and then somehow magically they're true much more generally. And as a general remark, there are no convergence issues in this kind of general setting. You just define the product of two power series by Cauchy's rule for evaluating the coefficients. That is, by definition, a new power series with those coefficients. So power series are just thought of as placeholders for coefficients or ways of encoding sequences rather than something that you evaluate. Now, Jacobi had a lot of mathematical insights, and they often start with very simple things like many insights. And one of his insights was that the 1 minus x inverse, which of course can be expanded in a geometric series, is the exponential of a logarithmic series. And that's what I call the X-blog trick. You know, X-blog is the identity map. You have any formula, you can apply, especially one involving products, try writing X-blog of it. And at first it doesn't feel like you've done anything, but then after you manipulate a bit, all kinds of nice stuff happens. So here's a totally trivial formula, and we write out the power series, and then Jacobi was not explicit about it, but implicit in Jacobi's paper from about 1840s is the idea that you could introduce multipliers. Here you have an obvious identity. So what happens if you introduce some multipliers, a U1 here, a U2 here, a U3 here, and you introduce some multipliers R1 here, R2 here, R3 here, and you consider this identity of power series written in the third line. Now, if you do that, it becomes clear very quickly that your UN coefficients are some polynomial function of the R's, and the Rn's are polynomial functions of the U's, and that this is a bijective correspondence of the nicest possible kind, meaning that, for example, I've only written 3 variables here, but these are 3 polynomial functions of these 3. Each of these 3 is the polynomial functions of these. And so it's sort of consistent. It sort of grows in layers. You can keep adding a new variable and you extend the correspondence that you already have. And I'll write down some almost trivial instances of the correspondence. The most trivial one, of course, is the one up here, which is that the sequence of all ones corresponds to the sequence of all ones in this bijection. And if you just replace x by a constant qx in this identity, you see that the sequence of powers, q to a power, is going to correspond to q to a power. So the fixed points of this correspondence are the power sequences. And this is mainly why I like to write this correspondence with the division by n in the nth coefficient on the right-hand side. That is almost entirely a matter of convention. You'll find people put factorials into these identities, but it doesn't make a big difference. the identities, in my judgment, look simpler and easy to understand and work with if you do them the way I propose here. And I write down a couple of other instances of the identities which come from familiar power series, or from instances of the correspondence. I'll talk a bit more about these as we proceed. So let me just show you in modern notation what Euler's derivation from 1755 is. We start with an exponential formula, which I like to write with the coefficients like this. And you just take that formula, you first differentiate it, and you multiply it by x, and you use the chain rule of calculus. So you just treat this as convergent power series, do calculus, differentiate under the integral sign, and see what happens. And you get this relation, and then you realize that this is an identity of power series, and you can write down the identity of coefficients of x to the n. And that gives you what I call the x-blog recursion, which is that the coefficient of x to the n here equals the coefficient of x to the n here. And that is that n(un) is the summation of rj un minus j 1 to n. And this is, recursion is carrying with it the convention that u0 is 1. And you should think of that as just a device for simplifying the recursion. And then the real thing, it's a relation between two sequences, u1, u2, u3, and r1, r2, r3, and it goes both ways. If you know the u's, you can figure out the r's. If you know the r's, you can figure out the u's. That's pretty obvious from the recursion. And then you can state a more or less formal theorem. So Euler's, what I call it, Euler's x-blog theorem, which has been, rediscovered by many mathematicians in many following centuries, usually without attribution to Euler, which is that the following facts are equivalent. One is the exponential formula as an identity of formal power series. Another is the logarithmic formula as an identity of formal power series, where both exp and log are understood in the obvious way in formal power series by their usual expansions. And of course, when most people, when they see expressions like this, they somehow think of this as relations of transcendental functions, or functional relations. But these relations are completely equivalent to a recursion, which is telling you how the UN sequence is gotten from the Rn sequence, and for that matter, vice versa. And as I've said before, this is a polynomial bijection from sequences of length n to sequences of length n, and that has all kinds of interesting properties and interpretations. And I mentioned a couple of corollaries of the theorem. So here's about four or five equations which are just logically equivalent. One is the x-blog recursion. Here is a more or less explicit way of saying what un is. You take this polynomial, raise it to the kth power, sum over k with weights k factorial, and then extract the coefficient of x to the n. That is some polynomial in the r's, and that's what un is. And you can completely invert this or flip this. This is how you get the r's from the u's recursively. And here's the explicit formula that rn over n is the coefficient of x to the n in another explicit polynomial expression. Now, these polynomial expressions are somewhat tough to work with. They don't really help you understand what is happening here conceptually, but they're extremely useful for computer algebra and formal manipulation. So I wrote down the first few polynomials explicitly. And so the relation forces u1 to be r1, then u2 is this. I've written down the polynomials for u1, u2, u3, u4, and also the inverted ones. You'll notice that the u's in terms of r's have rational coefficients because we are dividing by a factorial in here. The r's in terms of u's have integer coefficients. U's in terms of r's is easier because everything here is positive. Here you have some negative signs, which is more troublesome to interpret combinatorially, but again, for computer algebra, just fine. On both sides, both ways, you have one term in each polynomial for each partition of n. And it's easiest to, as I say, to understand what's going on in UN. If you want to know what, for example, what is the coefficient of R3, R1 in UN? So there's going to be a 1 over 4 factorial, which is there for everything. And you need to know where this 8 is coming from. Well, the insight of Jacobi from 1840, which is completely absent in Euler's discussion, is that the 8 is counting some permutations. The 8 is the number of permutations of 4 elements with 1 3 cycle and 1 1 cycle. And if you're looking at the R2, R1 squared, the 6 is the number of permutations of 4 things in which there is 1 2 cycle and 2 1 cycles. You'll find fairly extensive treatment of this stuff in more or less explicit formulas in Stanley's enumerative combinatorics. You'll find another take in my combinatorial stochastic processes from a few years ago. And the theory has been developed by many mathematicians, and I just mentioned a few famous names there. So I write down a few instances. The most almost trivial one is that the sequence Rn over n factorial is corresponding to the sequence R000. That's just the expansion of an exponential. A much more interesting one, which is a little puzzling at first, which is the sequence of binomial coefficients. You take a number R and then you take R choose n, or number, it could even be an element in your field or your Q algebra, and the binomial coefficient is by definition this falling factorial function. That function corresponds by the X-blog map to this alternating sequence of R's and minus R's. And the easiest way to understand that is to take another example, which is what Stanley calls the multi-choose coefficient. R multi-choose n is the number for R, a positive integer, the number of multi-sets of the set R of R elements of size n. And that's related to the binomial coefficients. In this way, the thing is simpler to deal with in many respects because it's a rising factorial instead of a falling one. That guy corresponds to the sequence R, 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 dot, dot, dot in the X-blog relationship, and that is nothing more or less than a fancy way of writing the negative binomial expansion. And here it is. I've written it precisely as the negative binomial coefficient. Use the multi-choose notation. You're just expanding 1 minus x to a negative exponent, and you say, well, that's x of R log 1 minus x inverse, and you write that out. And now you just see that inside the exponent, you're just seeing R, R, R as the additional factor over the 1 over j. And I mentioned before, I won't go through this slide in any detail at all. The fixed sequences in this bijection are the powers. That's very easy to check. So I mentioned now that some of the many probabilistic interpretations. What I find fascinating somehow is that there's not one probabilistic interpretation of the X-blog map. There's about 5 of them. I've mentioned most of the big ones on this slide. Moment cumulants, connection with Poisson infinitely divisible laws, their role in exponential families, their role as the cycle index of a uniform random permutation. They appear in moment polynomials, Wald and Wick polynomials. They appear again in renewal theory sequences, and as a special instance of that in the fluctuation theory of random walks and Lévy processes. So all bits of all of this stuff can be found in textbooks of probability theory, but there isn't any sort of common discussion or recognition of the common X-blog theme. And I mean, I feel like people should know about X-blog and understand it as the same thing appearing over and over again, and try and get it figured out once, and then see how it appears in these different contexts. So let me now be a bit more precise with my terminology. Just a little language for permutations, partitions, and compositions. I denote by square brackets n the set of numbers 1 to n, and I use n equals 8 in most of my examples. A permutation is a bijection from the set to itself. And I have written this permutation in Cauchy's cycle notation. That means that 1 maps to 2, maps to 4, maps to 1, 3 maps to 5, maps to 6, maps to 7, maps to 3, and 8 maps to itself. There's also usual 2-line notation for permutations, but the cycle notation is very congenial for many reasons. So a partition of the set 1 to n with k parts is a collection of disjoint non-empty sets with union, the whole set. And an example of such a partition, I just take my example, which was defining a permutation. I just put curly braces around it. And now I'm talking about the set of sets 1, 2, and 4 in one block, 3, 5, 6, and 7 in another block, and 8 in a third block. Now, a composition of n is just a sequence of positive integers with some n, and such a composition comes from this example. It would be 3, 4, 1. A partition of n is a composition where the parts are decreasing, or in another way, it's a composition where you ignore the order of the parts, and the standard way of writing the partition would be to write it as 4, 3, 1. And partitions are commonly encoded by numbers of parts of various sizes. I use an m dot notation to indicate a suppressed argument j, and the sum of j times the number of parts of size j has to be n, and the sum of the number of the counts has to be what I call k, which is the number of blocks in the partition. And there's a key enumeration, which is due to Jacobi and Cauchy independently in the 1840s, which tells you exactly how many partitions there are, how many permutations there are whose partition type with cycles is a particular sequence m dot. And there's the formula, it's n factorial over product j mj times j factorial, which most of you will be familiar. I've written it down here. It's written in the bottom right-hand corner here. Most of you will be familiar with this from the Ewan sampling formula, which is closely related. And this is a classical enumeration. And I just want to quickly mention what I find. Always found that formula a bit annoying and intimidating. And then one day I realized that it's just ridiculously easy and sort of lucky where that combinatorial formula came from. If you start with the following problem, how do you make a permutation uniformly distributed on the set of all permutations of n which have a particular cycle type? And the amazing thing is that the first thing you try works. And I just illustrate by an example. Suppose you want to get the partition which is commonly denoted 1 squared, 2 squared, 3, meaning that there's 2 parts of size 1, 2 parts of size 2, and 1 part of size 3, which is a partition of 9. So you write down the desired cycle structure with just sort of placeholders. There you have 2 1s, 2 2s, and a 3 for convenience in increasing order. And now you just fill in the blanks by a uniform random permutation of 9. So there's 9 factorial things that you could now write down. I've just written down one of them where this this particular permutation in row notation 4 2 7 3 1 8 9 5 6. Just fill in the cycles. And now you read that expression in Cauchy's cycle notation as a permutation. You say, well, we created the permutation 4 maps to 4, 2 maps to 2, 7 to 3 to 7, ... And then you count how many ways you could get exactly this result or this permutation, how many different permutations map to this by this method. And it's rather obvious what's going on. You could swap. Here you could have got these in 2 different orders. Here you could have got 3 maps to 7 maps to 3 instead, or and these 2 guys could be swapped. And here you could have started this cycle with this 9, with this 5, with this 6, or this 9. And due to that, you can just write down the number of ways that you would get this result. And then you realize in an aha moment that this number of ways is the same no matter which of the possible results you might have imagined. And once you realize that, you now realize that this particular map, which was just the sort of the first thing you tried, it's actually some number of to 1. And that number has to be the product of mj factorial j to the mj. Consequently, n factorial is the number that you would like to enumerate times this extra factor. So this is basically a double counting argument, which is almost, or it's very, very similar in spirit to how you enumerate n choose k as a ratio of factorials by double counting, but it's just a version of that for permutations and partitions. Now, I want to write down a couple of explicit summation formulas. I'm not going to go in this slide in detail, just to say that there are these formulas and that they're all rather easy by change of variable in summations. The first formula is the very Eulerian looking formula that you're just extracting the coefficient of x to the n in some exponential looking series. And then if you just get down to it, to extract this coefficient, you have a summation over all the different ways that you could choose compositions of n. The compositions can be clustered by partitions. The partitions can then be overcounted by permutations using the enumeration on the previous slide. And finally, you realize that you are just averaging a product over cycles of a permutation, and you get down to what I find probabilistically the most agreeable expression for un as a function of all the r's, which is that it's the expectation of the product of rj to the power kj of pi n. Pi n is a uniform permutation, and kj is its number of j cycles. And at this moment, you realize, oh, all we're talking about is the joint probability generating function of the numbers of cycles of a uniform random permutation of 1 to n. And that is somehow being encoded for us by this xblog recursion or xblog formalism. Yeah, so I've just written it down. I've written down the formula again. I'm just repeating what I said before here. It's a name, it's usually called the cycle index polynomial. And there's a very nice probabilistic interpretation of this polynomial, which is an instance of a general interpretation of probability generating functions, which is you can say, look, I have my permutation, I make a permutation, and then I'm going to delete cycles, or I'm going to try to delete cycles. I say each cycle of size j, I'm going to delete it with probability rj independently of whatever other cycles there are. Then this product in here is the probability that I retain it rather than delete it. I retain it with probability rj. This product here is the probability that I retain all the cycles. And so we get this very elementary probabilistic interpretation that un as a function of r1 to rn is the probability that you keep all the cycles of the permutation if you keep every cycle of length j with probability rj independently from one cycle to another. And I love this quote from Polya long ago. Polya understood that this cycle index polynomial was pretty useful, and he has this nice quote: "The cycle index knows many things." And indeed it does. It knows Euler's xblog theorem. It knows the moment cumulant correspondence. It knows about Bell polynomials, renewal theory, fluctuation of theory of random walks, compound Poisson processes, all kinds of things lurking in this rather innocent looking cycle index formula. So about theories built from the polynomial, there's another Polya maxim that I like about the mathematicians: the generalizers and the specializers. The generalizers are the monkeys climbing the trees, the specializers are the monkeys climbing down the trees. And Polya thinks that a real mathematician must be able to do both. I'm not sure what I think I'm some sort of paraplegic monkey or something. I'm not quite sure what I'm doing, but I like to, anyway. I like Polyer's maxims. He has full of maxims. He has his how to solve it, all kinds of insights about the mathematical enterprise. Yeah, so it's nice to understand what the recursion means in terms of the cycle index. So here's the recursion, and the recursion for the generating function is basically what you get by conditioning on the cycle size containing a particular element. So you convince yourself that if you have a uniformly distributed random permutation, the size of the element containing 1 is uniform. And once you've conditioned on that, when you look at this, the expectation of this product, you break off, here it is, you break off a single factor, namely the factor that you get from the cycle containing 1, and then you've got the remaining factors. But that once you know the size of the cycle containing 1, this first guy is an RJ. The expectation of the remaining factors is your function of the remaining variables, which is your UN minus J. And you have a simple arithmetic average because the size of the cycle containing 1 is uniformly distributed. Now, that shows you that the structure actually doesn't have to be said that much in terms of permutations, and I like to say it by a more naive scheme that I call discrete uniform stick breaking. So let me show you that model. We start with a stick which is composed with n segments, and I'm drawing it for n equals 8. These are labeled segments, 1, 2, 3, up to 8. I pick a segment uniformly. It looks like I picked number 3, and I break it to its right end, and then I forget the numbers. And now I have a remaining segment. I pick I have a remaining stick composed of several segments. I pick one of those segments uniformly and break it there. It looks like I picked segment 7, and I broke it, and now I'm left only with 8, and I've just got one stick left. So by basically recursive choice of uniform variables, I break my thing of size 8 into a piece of size 3, a piece of size 4, and a piece of size 1. And then I can ask, what is the probability that I get that? What's the probability that I get the result 3, 4, 1 by my stick breaking scheme? And the answer is it's 1/8 to get the 3. And then given that, it's 1/8 minus 3 to get the next 4. And it's 1/8 minus 4 minus 3 to get the last 1. And there's a 1 in 40 chance that you result in 3, 4, 1. Now, the stick breaking scheme is deliberately chosen to mimic the structure of cycle sizes of a uniform random permutation. So this is precisely the probability of the cycle sizes in order of least elements given in 3, 4, 1. And now you can see again with the sticks, you say for each stick of length j, retain it with probability Rj independently. The probability of retaining all the sticks is our polynomial. And the recursion is just by conditioning on the length of the first stick. And you just sort of, somehow the stick breaking really brings home the recursive structure, or very elementary probabilistic recursive structure of what's going on here. And as Lance and others well known, this discrete model of stick breaking has many variants and continuous analogs, and is a very rewarding thing to study more deeply in the setting of Bayesian non-parametric statistics, right, Lance? Breaking a geometric stick. This idea, I think, is due to Shep and Lloyd in the setting of permutations. And it's just a very simple idea, which is often very powerful, which is when you have some discussion of things of fixed size, and it's annoying that you're working always with the constraint that the sum of the parts is given. You liberate the size of the structure. In this case, you assign a geometric size to your permutation or your stick. And I use X as the parameter, which would usually be denoted Q for a probability distribution, or Q, which is a 1 minus P. And then I do uniform stick breaking on a stick of random geometric length. And then obviously by definition, my geometric variable has been decomposed into a sum of j times the number of sticks of length j. And now by design, these numbers of sticks are distributed like the number of j cycles in a uniform random permutation of a geometric number of elements, with a convention that you get nothing if you have no permutation, if g of x is 0. And now Euler's X-log theorem has the following probabilistic expression. The component counts are independent Poisson variables with means x to the j over j. And this formula 9 is the compound Poisson representation of the geometric. And as a sort of sanity check, you can compute its expectation. You say it's sum of j expected kj of x, and then that's a j times an x to the j over j. The j's go away, and you sum the geometric series, you get x over 1 minus x, which is, of course, what we know to be the mean of a geometric variable. Now, I want to remark that this result, or this way of framing it by Shepp and Lloyd, is essentially the same as what I would call Euler's X-log theorem, though it's often not always recognized as such. So the identity that I would say is sort of Euler, Jacobi, Cauchy, or perhaps with a little bit of Polya, is that you have this basic interpretation of the X-log relationship, which is the Polya cycle index expression. You have this rather trivial formula, which is that 1 minus x is exponential of its own logarithm, and you expand the log. And you multiply these two formulas together, and you see that this slightly modified formula must hold. And now you recognize that the right-hand side, this piece of it, is interpretable as the expectation of a product of RJs to Poisson powers. You are looking at the Poisson probability generating function when you've got to this right-hand side. So in my expression here, the nj of xj over j are independent Poissons with means xj over j. And that's just because of the familiar power series form of the Poisson distribution. So this is somehow how you get Poisson variables into the story, is you recognize the formal power series of Euler and the expression in terms of geometric stick breaking, and you see that you are expressing an independence of counts of different cycle sizes when you randomize the size of your permutation. So I have a slide with an example of fixed points. I think I'll maybe skip over this because it's very close to textbook treatments of how you find the distribution of number of fixed points of a random permutation. And that's basically, in the general discussion, you just take your R sequence to be R1111 and see what happens. And you see in particular that you get a Poisson 1 limit for the number of for the number of fixed points in a uniform random permutation. And Shepp and Lloyd exploited this and to discuss all very similar things, to discuss also the longest cycles, second longest cycles, etc. And for the full story along these lines, you should open the text by Aratia, Barber, and Tavare. Logarithmic combinatorial structures goes way, way further than anything I've written on this slide. Independent cycle indicators, I'll skip that too, because that is also very, very easily found in the ABT book. But I'll just mention an enumerative interpretation, which is somewhat different from the probability interpretation. From previous discussions, if you evaluate the cycle index at all constant R, you get the probability generating function of the number of cycles of a uniform random permutation, and that's Stanley's multi-choose coefficient R multi-choose n. R into R plus 1 and n factors divided by n factorial. In this instance, if you have r's that are positive integers, you get a positive integer out as your evaluation of a polynomial. In general, it's not true. The UN polynomial has rational coefficients, and you don't always get integers out. However, if you multiply by an n factorial, you always will get an integer. You've just replaced an average by a sum of the permutations. This is what Stanley calls the augmented cycle index in his second volume. And now you have a completely enumerative interpretation of this function. N factorial times the polynomial is the number of ways to first pick a permutation and then color each of its cycles of size j by one of r sub j colors. If you take that interpretation, you realize you are very, very close to the definition of Bell polynomials, and essentially modulo bookkeeping with factorials, Polya's cycle index generated by the X-blog recursion. It is an encoding or a variation of the Bell polynomials, and here's an explicit formula that shows you that. The Bell polynomials are most easily understood as sum over partitions of products. And Bell polynomials are nice, if only because they're in computer algebra packages, and I'm not sure that the cycle index is. But you can get the cycle index by just substituting in the Bell polynomials, for example, in Mathematica. Now,
Jim,
yep.
Just to let you know, you have about 5 more minutes.
Yeah. So thanks. In another vein, there's the moment cumulant correspondence, which involves the same mathematics but very different interpretations. And this is probably familiar to almost everybody, which is that you can you can expand a moment generating function with moments and write it as exponential of a cumulant expansion. And so what is usually called the moment cumulant correspondence is, in my language, the X-blog relation between mu n over n factorials and some things that are called cumulants normalized by j minus 1 factorial. So up to multipliers with factorials, there's no real difference here. And what I've called Euler's X-blog recursion, which was discovered in 1755, is Thiele's recursion, which was Thiele did not discover until 1890, right? So sort of these ideas, they seem easy now, but it took 150 years to sort of, to move from a calculus text, which had it all laid out, to, oh, that's what you need to do to swap back and forth between moments and cumulants. And I just mentioned that in this setting, I mentioned before that it's useful to know that what the fixed points of the bijection are. We said the fixed points were powers when you used my conventions or the Polya conventions. And in this case, if you ask, well, what happens when you have something whose nth moment over n factorial equals its nth cumulant over n minus 1 factorial? Well, that happens if and only if the nth moment is n factorial times the first moment to the nth power. And that's just saying that x is exponential with mean mu1. So you have this sort of one parameter family of probability distributions, which is the exponentials with different means. And that's corresponding to the fixed points in what I'm calling the X-blog correspondence. Well, I'll skip the normal distribution. Everybody knows the moments of the normal distribution. I just mentioned that there are lots of combinatorial interpretations of normal moments in terms of matching, and papers by Godzil, Janssen. And this ties in with Wick powers and so on. What more to say in a few minutes? Power series distribution, well, a little bit of maybe discrete renewal theory. Yeah, I just mentioned that let's look at infinitely divisible distributions. This is from Levy-Khinchin and also Katy in the 1960s. Suppose you have y of x, which has a power series distribution 1 plus u of x. So that just means that this is the probability generating function up to normalization. And then you have a UN sequence, and suppose it corresponds by the X log map to an RN sequence. Then the following are equivalent. One is that the RN sequence is all positive. One is that the power series distribution is infinitely divisible for some X, or it's infinitely divisible for all X. And then you have this explicit description of the infinitely divisible variable as a compound Poisson variable, and it's just a modification. It's like a perturbation of the geometric representation that we discussed before, which came from the random permutations. In the geometric case, the RJs are all identically equal to 1, I think. So it's just a slight perturbation of this construction where you introduce these extra multipliers, and you've turned the compound Poisson representation of a geometric variable into the compound Poisson representation of a general infinitely divisible power series distribution. And I mentioned the place to look for that is the book of Stoitel van Harn. And I just maybe compare, contrast in this to see these things showing up in renewal theory. In renewal theory, anyone who's read Feller Volume 1 will be familiar with this type of recursion relating a renewal sequence UN with first return probabilities Fj, and that may be compared with what I call the Euler recursion, which looks awfully similar, but you've just got this 1 over n stuck in the middle. You're taking an average instead of a sum, and then you can write all these formal relations, or you can compare, contrast them, and see that the renewal sequences are really very much bound up with infinitely divisible laws, and perhaps way beyond. Do I write it? Write it. Yeah, it's this sentence. If you have a renewal process, then the last renewal up to an independent geometric variable is a compound Poisson distributed random variable. So that's a way to get a large class of infinitely divisible laws is just to run a renewal process, stop at the last renewal before your independent geometric, and you have a generalization of this scheme of the geometric itself being compound Poisson, where you get your last renewal up to a geometric as compound Poisson. I should perhaps stop there. I have certainly there's more to be said on this topic. It's somewhat difficult to restrict the scope of a discussion of the Eulerian elephant. I hope I've at least showed you a few of pieces of the anatomy. There are more pieces that I haven't mentioned. There's more branches of probability theory or themes, and also combinatorics and geometry, where the Eulerian octopus has its tentacles, to use another animal metaphor. And I encourage you to come to appreciate the depth and interests of Euler's 1755 calculus text.
All right, thank you, Jim. Okay, so yeah, there's a lot there. Do people have questions? I can start. So yeah, there was a lot going on there. I mean, in your talk, it seemed like we have this identity, and then you've identified places where it sort of has come up, but maybe you could say something about like a little bit more about the applications in some of those settings, or like, just choose one or something where, okay, once you have this identity, it allows you to do something that you wouldn't have been able to do kind of more directly, or something like that.
That you wouldn't, well, the fact is that in most of these settings, people have just done stuff without even realizing that they were working around this Xblog theme, right? They just sort of did the math and got the results that they wanted. So certainly many of the, I mean, in the combinatorics of permutations, I don't know if you call it an application. I mean, the fact that the cycle counts are asymptotically independent Poisson variables, that's a very significant result in the combinatorics of random permutations. So that was discovered, I forget exact, I believe it was discovered by Goncharov in 1945. So it's somehow interesting how long it took that fact, that rather simple to say probabilistic fact, to be discovered, considering how many mathematicians had been working on variations of the Euler Xblog theme, Bell polynomials, Polya, Touchard, etc. in the 30s, right? So also the Shepp-Lloyd results. I mean, Shepp-Lloyd gave a pretty definitive account of the long cycles of and also some aspects of the short cycles of random permutations. They did their asymptotics, and basically the Xblog formula, or its expression in terms of independent Poisson counts of cycles of different sizes, was the beginning of everything they did. Yeah. So this is there's any number of applications, right? And the material I'm talking about is very foundational. And what I'm trying to do is to make the point that if you get this foundational stuff right, it's actually rather easy, right? It's easy when you say it right. These things can seem much more difficult and much more opaque when they're not organized in something like the way I would propose to organize them.
Yeah. Okay. Yeah. Thanks.
Maybe, I mean, and Andrew can comment on this. I mean, Andrew is thoroughly familiar with much of what I've said in the context of cycles of permutations, and not to mention compound Poisson, which he's worked on plenty.
That's right. Yes, I mean, some people have made parts of their careers based on the Xblog, if you look at it that way.
Yeah, exactly.
Yes, we tried hard to get these combinatorial things written in probabilistic terms when you wrote the book. I think that was one of the things, just to see that in probabilistic terms, some of these things look actually very natural. In ways that they're sort of mysterious when they're looked at analytically. But that, of course, is partly a matter of taste too.
Other questions?
May I ask a simple question? So you explored the relations between log and exponent, and it could be some other relations between other functions. Do you think which one is probably, in your opinion, would be the next one so important as that one?
Well, undoubtedly, so the discussion of Xblog in combinatorial terms of formal power series, it fits in the framework of what is called the compositional formula. You'll find that in Stanley's enumerative combinatorics. What is remarkable is that to state or to formulate a general compositional formula for essentially arbitrary power series for which it makes sense, the pieces of the formula are all the pieces that you get out of the Xblog, right? The Bell polynomials, right? So you can see all the special polynomials that you get by different compositions of functions. So you get, powers, log, exp. Certainly those are the main. The next main one is powers. But all the special kinds of potential polynomials and so on, they are almost all instances of a compositional formula, and the fundamental building blocks are the polynomials that you get out of the Xblog paradigm. They all come from sums over partitions, and the leading special case from which everything else can be constructed is the Xblog case. And you see that, I think, pretty clearly. This insight, I think, is perhaps due to Bell, who developed Bell polynomials. I mean, Bell basically defined his polynomials by the X-log relation, and then observed that once you have these, well, now you can do all these other things. So the answer is you can do very general composition discussion. There is a thing that's called the compositional formula of combinatorics. And if you look in Stanley Volume 2, how he presents it, you'll realize that the basic building blocks are these the Bell polynomials, which satisfy a certain recursion, and the recursion is basically the X-log recursion.
Thank you.
So I certainly haven't explained that in detail, but I think you will realize that if you go and look in these other sources.
Other questions? Okay, well, if not, let's thank Jim again for a very nice talk. Yes.
Thanks.
Okay, great. Thanks,
Oh,
everybody.
welcome. I mean, glad to linger and chat with anyone that wants to. I can get rid of my. I suppose I stop share. There you go. Then I should have done that already.
Yeah, that's fine.